Picture this, right? You're walking out of the bitter, freezing Cambridge, Massachusetts winter.
Oh, yeah, that wind just cuts right through you.
It really does. And you are stepping into this massive, incredibly intimidating MIT lecture hall.
Hmm.
You grab a seat, pull out your notebook and look down at the syllabus. The date is January 2010.
Wow.
And you've just walked into course 6.092, Introduction to Programming in Java.
It is quite the scene to put yourself in, honestly. I mean, you are sitting there surrounded by some of the brightest minds. The room is completely silent, and you're all just like waiting for the professor to walk in and demystify this machine sitting on your desk.
Exactly. And the stakes for you today are incredibly high because the mission of this deep dive into these specific MIT course notes is to, well, extract the absolute core mechanics of how humans actually communicate with computers.
Right.
The promise of this course is that by the end of it, you won't just know theory. You're going to learn enough Java to do something genuinely useful in the real world.
And they define useful with some very ambitious examples right out of the gate.
Yeah, they do.
I mean, the syllabus mentions manipulating PDF documents, drawing complex graphics on a screen, and this is the big one we're really going to be building toward today, simulating a natural physics process.
Which is just wild for an intro class. Because I'm looking at the logistics outlined in these notes, and the pacing is a complete gauntlet.
Oh, absolutely.
This isn't like a relaxed seminar. The assignments have to be submitted online through their system called Stellar, and they are due at 3 p.m. the very next day.
A 24-hour turnaround.
Right.
To build a working program, potentially for someone who has never written a single line of code in their entire life, that forces a very specific kind of learning.
It forces survival mode, is what it does. You can't just sit in the back and absorb the theory. You have to produce working software immediately.
Yeah.
And to even pass the class, you must make a reasonable attempt on 6 out of the 7 assignments. It really sets the stage for our journey today. We have to figure out how this communication bridge works, and, we have to figure it out fast.
Which means we need to strip away all the software for a moment and start at the absolute foundation.
Okay.
Before you can write a line of code, you have to fundamentally understand what you are actually trying to command. We have to look at the raw hardware.
Right. And the notes provide this incredibly clean, stripped-down diagram of computer architecture to start things off.
Yeah, the classic box diagram.
Exactly. You have this box in the middle called the Central Processing Unit, the CPU.
Mm-hmm.
And the CPU is constantly passing information back and forth with 2 other boxes, memory and input-output devices, which is like the keyboard you type on and the screen you're looking at.
Right, the CPU is the engine of the entire system. It's doing all the actual processing. But there is a massive misconception about what a CPU actually is.
Oh, totally.
We tend to think of it as this brilliant electronic brain.
Yeah.
Right. But the instructions it inherently understands are shockingly primitive.
I'm looking at this hardware limitation, and there's just a massive gap between what we think computers do and what they actually do.
Yeah.
Like if I'm writing code to build a website, the CPU doesn't know what a website is.
Not at all.
The notes show a CPU instruction is literally just read the voltage at location X, read voltage at location Y, add them together, rate the new voltage to location Z.
Exactly.
It's just shuffling tiny microscopic pieces of electrical data around in physical memory.
That is the fundamental disconnect. I mean, the CPU is incredibly fast, but it is incredibly literal and entirely devoid of context. It operates purely on basic arithmetic and memory retrieval.
Okay, let's unpack this, because if I want you to walk across the room and hand me a cup of coffee, I just say, hey, could you grab me that coffee?
Right. I know what coffee is. I know where it is.
Exactly. You understand the goal. But if you had the processing logic of a raw CPU, I couldn't give you the goal.
No.
I would have to say, fire the left calf muscle at 20% capacity.
Mm-hmm.
Shift your center of gravity 3 degrees. Engage the bicep to extend the arm.
Yeah, giving instructions directly to a CPU is like telling someone how to walk by commanding every individual muscle twitch.
It's insane.
It's a perfect way to visualize it, really.
Yeah.
It's way too complex, tedious, and error-prone for any human to do efficiently.
Right.
And this is exactly why programming languages had to be invented. We needed an abstraction layer. We needed a way to issue the high-level human command like, get the coffee, and rely on something else to automatically break that down into the thousands of microscopic muscle twitches the CPU requires.
And in this intimidating MIT hall, that abstraction layer is Java.
Yes.
And the notes place it on a very specific spectrum of complexity, sitting right between Python and C++ Sorrent.
What's fascinating here is that it sits in this really powerful middle ground.
How so?
Well, Python abstracts almost everything away,
Yeah.
right? Making it very easy to read,
Mm-hmm.
but sometimes hiding the underlying mechanics. But then C++ forces you to manually manage the computer's memory, which is powerful but super dangerous if you make a mistake.
It could crash the whole thing.
Exactly. So Java strikes a balance. It handles the messy memory management for you, but still forces you to structure your logic very strictly.
But wait, if I'm typing English-looking words into a Java file, and the CPU only understands those binary voltage changes, those muscle twitches,
Yeah.
there has to be a heavy-duty middleman doing the translation.
Oh, absolutely.
Because our human-readable code doesn't just magically execute.
It definitely doesn't.
Hmm.
And Java handles this translation in a very unique way. It's not a direct one-to-one translation from your code to the CPU.
Okay.
It actually utilizes a highly specific two-step pipeline.
Right, and the notes map out this compiling process. Here's where it gets really interesting, because it reminds me of publishing a book for a massive international audience.
Oh, I like that.
Yeah, so you write your original code in a file called source code, ending in .java. That is your original manuscript in English. It's perfectly readable to the programmer.
But entirely useless to the silicon inside the machine.
Right. So you run that .java manuscript through a tool called a compiler. In Java, this specific compiler is called javac.
Yeah, Java.
And this compiler takes your English book and translates it into a rigid, universal intermediary language. The notes called the stage bytecode, saved as a .class file.
Exactly.
So in the publishing analogy, javac just translated your English manuscript into Esperanto, like a universal language.
It is highly structured, mathematical, and optimized. But the catch is, it is not native to any actual machine.
Wait, really?
Yeah. A Windows CPU cannot read bytecode. A Mac CPU cannot read bytecode.
Oh, which brings us to the second step.
Yeah.
You have this Esperanto book, this .class file. To actually run the program, you hand that file over to a piece of software called Java, which acts as a virtual machine, or JVM. The JVM is like a highly trained local interpreter. It reads the Esperanto book out loud, instantly translating it on the fly into the native specific dialect of whatever local CPU you happen to be using at that exact moment.
That two-step architecture compiling to bytecode, then interpreting through the virtual machine, is arguably one of the most brilliant software engineering decisions in history.
Really?
Oh, yeah. It enables a philosophy called write once, run anywhere.
Ah.
The programmer writing the original Java code never has to worry about what physical hardware the end user has. They don't care if you're running a 10-year-old laptop, a brand new smartphone, or a massive Linux server.
Because the programmer only ever talks to the virtual machine.
Exactly. The virtual machine takes on the entire burden of dealing with the messy, localized translation to the specific CPU.
I see the brilliance, but surely there's a catch, right? Doesn't adding an entire intermediate step, like a real-time translator, make the program run slower than if you just translated it directly to the CPU's native language from the start?
You've hit on the classic trade-off in computer science. Yes, historically, running code through a virtual machine incurred a slight performance penalty compared to a direct compile language like C++Ben.
Okay.
But the trade-off was almost always worth it. I mean, the time saved by not having to rewrite your entire program for Mac, Windows, and Linux separately vastly outweighed a minor hit to processing speed.
Makes total sense. Okay, so because the JVM requires such a strict Esperanto translation from the compiler, the English we write in the original .java file can't just be casual, free-flowing text.
No, not
It
at
has
all.
to be incredibly rigid so the compiler knows exactly what to do. Let's look at that rigidity. The notes walk us through the anatomy of a first program, the classic Hello World.
Oh, the rite of passage. And even for a program that does absolutely nothing but print 2 words to the screen, the scaffolding you are required to build around it is substantial.
I'll say, you can't just type print hello world.
Nope.
First, you have to declare a class. The notes show class hello, followed by a curly bracket and open a block of code. Then inside that, you have this incredibly dense line. Public static void main string arguments. Why do we need all of those words just to start a program?
Every single word there is a strict instruction to the virtual machine. Public tells the JVM that this specific section of code is visible from the outside, meaning the system is actually allowed to access it.
That makes sense. If it were hidden, the program could never launch. What about static?
Static is a bit more nuanced, but essentially it tells the machine that this code can be run immediately without having to build any complex virtual objects first.
Yeah.
It's the primer.
Okay.
And void simply means that when this program finishes running, it shouldn't try to send any mathematical data back to the operating system. It just executes and quietly closes.
So public static void man is literally the front door. The
Exactly.
JVM aggressively scans the file for that exact phrase to know where execution begins.
Yep.
And then, nested inside all of that protective scaffolding, we finally get the command that does the work. System.out.println hello world. The notes specify that this command targets the system's output console and prints whatever text is locked inside those quotation marks.
It feels like a massive amount of overhead for a simple task, but that rigid structure is exactly what prevents massive enterprise-level applications from collapsing under their own weight.
Well, and if we are going to simulate a real engineering process like the syllabus demands, printing text isn't enough, right?
Right.
We have to be able to remember things. We need to store data dynamically. And the notes introduce the concept of variables and types to manage the computer's physical memory.
Yeah, a variable is essentially a named location in the computer's memory that stores a value you want to keep track of.
We often hear variables described as tiny storage lockers in the computer's memory, but based on these notes, that metaphor feels a bit too loose.
Yeah, I'd agree with that.
It's more like a highly restrictive physical shipping container. You don't just rent a container. You have to declare exactly what shape and size it is. You have to declare its type.
And Java is incredibly strict about these types. The notes list 4 primary ones you'll use.
Okay, let's hear them.
Boolean is strictly for a logic value, true or false. Int is for integers, meaning whole numbers with no fractions, like 0, 1, or -47.
Got it.
Double is for real numbers, anything requiring a decimal point, like 3.14. And finally, string, which is a container specifically shaped to hold text.
So you declare a variable by stating the type, then giving it a name, like typing string course name. You are telling the computer, I need a text-shaped container in memory, and whenever I say course name, that's the container I'm talking about.
Exactly.
Then you can assign a value to it using an equal sign, like course name AAP 6.092.
Or, as the notes show, you can do it all in one highly efficient line. Double bad pi equals 3.14. You carve out the memory space, name it, and fill it simultaneously.
So what does this all mean? I understand the efficiency aspect. Like a tiny Boolean true-false switch takes up way less physical silicon in the memory card than a massive paragraph of string text.
Right.
But if I'm just storing data, why is Java so aggressive about making me declare the type? Why does the computer care if I put a number into a text container?
It cares because the type doesn't just dictate the size of the container. It dictates the fundamental rules of engagement for that data.
Rules of engagement.
Yeah. The compiler acts as a ruthless bouncer.
Mm-hmm.
It looks at the type to determine what kinds of operations are legally allowed to be performed.
Ah, so it's a safety mechanism.
Precisely. You can logically divide an int containing the number 10 by another int containing the number 2. The CPU can process that.
Sure.
But you cannot mathematically divide a string containing the word apple by a string containing the word banana.
Right.
The CPU would crash trying to compute that.
Yeah.
By forcing you to declare types up front, the compiler can scan your code and stop you from doing something disastrous before the program even attempts to run.
That bouncer stops the crash before it hits the hardware. I love that. Now, storing data in these highly regulated containers is just the prep work. To achieve the MIT goal of simulating physics, we have to manipulate that data. We have to do work.
And that introduces operators, the actual symbols that instruct the CPU to perform computations on our variables.
And it's interesting because the computer isn't smart enough to figure out context, so it enforces mathematical rules rigidly.
Oh, very strict.
The notes emphasize that Java strictly follows the standard order of operations. Parentheses are resolved first, then multiplication and division, and finally addition and subtraction. It doesn't just read left to right.
The syllabus demonstrates this sequential logic with a great snippet where they assign multiple variables. They show how you can calculate a value, store it in a variable, and then immediately use that variable to calculate something else.
Let's trace that logic because it shows how memory actually updates. They declare a double variable named score and assign it the result of a math problem, 1.0 plus 2.0, 3.0.
Okay.
Because the compiler enforces the order of operations, it multiplies 2 and 3 to get 6, adds the 1, and stores 7.0 inside the score container.
And notice it's 7.0, not just 7, because it was declared as a double.
Right, precision matters. Then the program creates a new variable, double copy score. It literally reaches into the score container, reads the 7.0, and copies it into a brand new container named copy.
Then they instruct the computer to manipulate the copy.
Yeah.
They write copy 2.0.
This is where the sequential nature of code clicks. It takes the current value inside copy, which is 7.0, divides it by 2, and overrides the old value with the new result, 3.5.
Right.
If you print the variables to the screen at the end, copy spits out 3.5, but score still safely holds 7.0, you are actively managing state over time.
And there's one fantastic quirk with operators in Java. If you use the plus sign on numbers, it does addition.
Obviously.
But if you use the plus sign on string types, it performs something called string concatenation.
Which means it just glues the text together.
Exactly.
If you type hello plus world, the compiler understands the context of the container and just smashes them into a single phrase. Hello world. You can even mix them like the answer is almost plus 42, and Java is smart enough to convert the number into text and glue it all into one sentence.
That ability to store data, strictly define its rules, calculate new values sequentially, and glue the output together, that leads us directly to the climax of this lecture.
The gravity calculator.
Yes.
The assignment these students have to submit to the Stellar system by 3 p.m. tomorrow.
And the prompt is daunting for a first day. Compute the position of a falling object over time.
They give the students the raw continuous physics formula. It calculates the final position of an object based on its starting height, how fast it's already falling, and the steady accelerating pull of gravity. But you can't just hand an algebra equation to a CPU and expect it to understand.
If we connect this to the bigger picture, this assignment perfectly encapsulates the lecture. It forces the student to synthesize everything we just talked about.
Yeah.
You have to take the continuous, fluid nature of real-world physics and translate it into discrete, sequential muscle twitches for the CPU.
I'm just imagining the friction of actually trying to write this. First, you have to allocate the memory. You need variables for time, initial position, initial velocity, and gravity.
And you have to make the crucial decision about types. An int won't work here.
No.
Gravity on Earth is roughly 9.81 meters per second squared.
Yeah.
You need decimal precision. So every single container must be rigorously defined as a double.
Right. And once the memory is set up and the values are loaded, you have to manually map out the physics equation using Java's strict mathematical operators. You have to ensure your parentheses are perfectly placed so the multiplication of gravity and time happens before the addition of the starting position.
You are effectively freezing time, grabbing the data from your restricted containers, running it through the CPU's tiny logic gates, updating a new container with the result, and finally using string concatenation to print a human-readable sentence to the console like the object's position after 10 seconds is.
It is wild to think about the mental leap required here. I mean, we started this deep dive looking at a diagram of a CPU that only knows how to move electrical voltage between microscopic circuits.
Yeah.
We saw how Java creates a rigid two-step abstraction layer using the compiler and the virtual machine to hide that hardware. We explored how the compiler acts as a bouncer, forcing us to use strict types to carve out memory safely.
And by chaining together those incredibly basic operations, assigning variables, multiplying, adding, and updating memory sequentially, we trick that same dumb silicon into accurately simulating the fundamental laws of physics.
It fundamentally changes what the word programming means. You aren't teaching a machine to understand physics. You are breaking physics down until it fits into the machine's tiny worldview.
Which is exactly the thought I want to leave you with today. This raises an important question.
Okay.
We just walked through how a physics simulation of a falling object is, beneath the surface, nothing more than a carefully orchestrated sequence of variable assignments and basic grade school arithmetic.
Just millions of tiny read, write, and add commands happening in the dark.
Exactly. So extrapolate that upward. If a complex physics simulation is built entirely from these microscopic steps, and by extension, the massive social media apps, the photorealistic video games, the operating systems that run the global financial markets.
Wow.
If all of the software you interact with every single day is ultimately built from these exact same primitive building blocks, how does that change the way you view the digital world around you?
That is a staggering perspective.
The next time you open a beautifully animated, seamless app on your phone, look closely at it. Ask yourself, is that sleek interface just a highly orchestrated illusion? Are you really just looking at billions of tiny, rigid mathematical operations executing sequentially in memory, dressed up to look like a cohesive
You
world.
walk out of that intimidating lecture hall into the freezing Cambridge winter, and suddenly the entire digital world just looks like a massive churning matrix of variables and logic gates. Well, thank you so much for joining us on this deep dive into the true foundations of code. Take that perspective with you, keep exploring those underlying mechanics, and we will catch you next time.